Hello everyone, welcome to this lecture video for Math 116, Combinatorics, and we're going to talk about something called the inclusion-exclusion principle. So suppose we're given some sets, S1 through Sn. There's a question, which is how do we find the cardinality of their union? What we've considered already is what happens if we have a bunch of sets that are mutually disjoint, meaning they have absolutely no elements in common. And in that case, to compute the cardinality, all we have to do is sum up the cardinalities of each of the sets. But there's a problem in general, which is that sets don't have to be mutually disjoint. They might have some overlaps, so the intersections of different sets might be non-empty. So the inclusion-exclusion principle is a technique that we can use to compute the union of a bunch of sets by looking at cardinalities of a bunch of different kinds of intersections, as we'll see. So let's look at an example of how this problem can appear. So let's have A be the set 1 through 4, so it's this 4-element set, and let's let B be this 3-element set, 3 through 5. And if we were being naive and tried to compute the cardinality by adding together the cardinalities, we just do 4 plus 3, which is 7. But A union B, that's just the numbers 1 through 5, which is a 5-element set, and 5 is not 7. So what went wrong? Let's consider counting, so A plus B, or A union, the cardinality of A plus the cardinality of B. Let's see how we can represent that. So when we counted up the cardinality of A, let's put a little dot next to each of the numbers that we count, and so that's 4. And then let's take 3, 4, and 5 and put a dot next to those numbers. And so if we look, we have 1, 2, 3, 4, 5, 6, 7 dots, which is 4 plus 3. And we can see that what happened is that we attributed too many dots to the numbers that are in the intersection of A and B. So what we can say is that, well, 5, while it might not be 4 plus 3 directly, if we then subtract off 2, which is the cardinality of the intersection, then we have solved this problem of being a little too naive. And so the two-element set version of the two-set version of the inclusion-exclusion principle is that you just sum together the cardinalities of the sets, but then you correct it by subtracting the intersection of the sets. And so this is inclusion and then exclusion, hence the name of the principle. So what I want to do is prove the inclusion-exclusion principle, and for more general cases where you have an arbitrary number of sets. And to do that, I want to introduce the Iverson bracket. So the Iverson bracket is this link between logic and algebra, where, so I'll just give you the definition so you can see. So P, we're going to have that be some proposition, which recall a proposition is some statement that's true or false, and brackets around P, that's the Iverson bracket, is 1 if P is true and 0 if P is false. So we're turning true versus false into 1 versus 0. And it enjoys some nice properties. So for example, the Iverson bracket of a conjunction, and P and Q, ends up being P times Q, or you can write it as the minimum of P and Q in brackets. And a proof for this is simply we go through all the possibilities. So we've got true versus false for P and Q. And how does and work? Well, a true thing and a true thing is true. A true thing and a false thing, that statement is false. False and true is false, and also false and false is false. But we can also consider the multiplication table of x versus y. So yeah, let's write that as xy with 1 and 0 for the numbers, And if we just write this multiplication table out, we can see that there is a correspondence where trues become 1 and falses become 0. So that's true. It also has a formula, which is that's the maximum of the two. Because if either of them is 1, then the whole thing is 1. And if both are 0, then it's 0. And you can check that this formula holds. But we're going to check it in another way in the next slide. And another is that the negation, the logical negation, so the Iverson bracket of not P, is 1 minus the Iverson bracket of P. So you can see all the basic logic can be turned into algebra. Yeah, this is, if you've heard of Boolean algebra, this was his idea way back in the 1800s. So De Morgan's law, by the way, remember, is the negation of a conjunction is the disjunction of the negations, and also the negation of a disjunction is the conjunction of the negations. Just putting it down to so that we can look at it. Because let's look at how we can try to algebraically turn P or Q into the expression we saw on the previous slide. So I'm just going to introduce a double negation, which doesn't do anything, because not true is true and not false is false. And then with the outer not, I can pull out a 1 minus. And then for the inner not, I'm going to apply the second of these De Morgan's laws to get the Iverson bracket of not P and not Q. But it's an and, so I can turn that into a multiplication. And then each of these nots can be turned into 1 minus. And then if we multiply it all out by foiling, well, the 1 will get canceled out, and we're left with Iverson bracket of P plus Iverson bracket of Q minus the product of the Iverson brackets of P and Q. Or which, if we wanted, this thing could also be written as the Iverson bracket of P and Q. And if we think about it, this is a sort of the inclusion exclusion, because to calculate P or Q, let's say that just P, if just P was true and Q is false, then what happens is that we get 1 plus 0 minus 1 times 0. And so this last term doesn't do anything, and we're just left with 1. But if they're both true, then what happens if we get 1 plus 1, which is 2, which overcounts, and so we subtract off 1 times 1 to get the value back to being 1. So again, it's like inclusion, exclusion. So let's look at the two-set formula again in terms of the Iverson bracket as a warm-up. So the cardinality of a set, we can write it as the sum over all x of the Iverson bracket of x being an element of that set. So this is what's known as an indicator function, which is 0 if x is outside the set and 1 if x is in the set. And so then the point is that for every element in the set, this Iverson bracket is contributing 1 copy of 1. So they all add up to the cardinality of the set in question. Okay, so let's remember the definition of union. That is that x is an element of the union if and only if x is in the first set or x is in the second set. And then we calculated how OR works, so we can turn this into inside the sigma, the x is being the Iverson bracket of x in S plus the Iverson bracket of x in T minus x in S times x in T. And recall this is a product, so it's an and then the definition of intersection is precisely that the element is in both of the sets. Okay, so then when you have a sigma of sums and differences, you can distribute it over into each of those, and then notice that the first thing is the cardinality of S, the second thing is the cardinality T, and then we're subtracting off the cardinality of S intersect T. So what about multiple sets? So let's say that we have S1 through Sn that are sets, and we are looking at the cardinality of their union. So by that same trick, we can turn it into a sum over all x of x being in any of them, using the definition of union. And then using a generalization of what we did for a single OR, we can turn it into this big expression. So let's just puzzle through what's going on here. So this Iverson bracket, its definition is that if all of them are false, then the value is 0, and otherwise the value is 1. So let's think about what happens if each of these statements is false. Each of these, x is not an element of any of the sets. Then each of these are equal to 0, each of these Iverson brackets, and then we're doing 1 minus 0, so we get 1 times 1 times 1 times 1, and so on. And that evaluates to 1, and then 1 minus 1 is 0. So in that case, this expression matches up. Now what happens if any one of these is non-zero? I mean, any one of these is true. Let's just say, what if x is an S1? And in that case, the Iverson bracket here evaluates to 1. 1 minus 1 is 0. And 0 times the rest, it's 0. And then 1 minus 0 is 1. So, anyway, if x is an S1, then the Iverson bracket is 1, and also this expression is 1. And, x could have been in any of them. And for each of those cases, the Iverson bracket evaluates to 1. So, okay, I just walked through that as just checking it basically using a truth table. But really, it is doing the exact same sort of expansion for a single OR case, but you just keep going. Now, foiling you're familiar with. You might not be familiar with foiling when it's more than two things. And so the way that works is we consider the fact that when we multiply it out, what we can do is think about this as making n different decisions. Are we taking the first term in this binomial thing, or are we taking the second one for each of them? And so like we might take 1 here, we might take 1 here. For the next one, we might take x as an element of x S3, the negative of that, and so on. So a way that we can record our choice for every possible multiplication of this is as a subset of oh, I made a little mistake in my notation here, because in class I've been using square bracket n to mean to mean 0 through n minus 1. So I'm just gonna annotate this as here n equals 1, 2, 3 through n. So for every possible subset of these of 1 through n, that corresponds to a different choice of which of the two things we chose for each element. And the set is going to be representing, did we choose the second thing in each term? Namely, did we choose the negative Iverson bracket? And then for that choice, to calculate what that particular expansion was, we can then take the product over all elements of that index set of the things that we chose. And then for everything outside that set, we chose 1, and so we don't need to put it in because we're just multiplying a bunch of 1s together. Okay, so that's so that's the formula for this sort of expansion. And then we can take this and break up the sum into a two-step procedure. Instead of just summing up over all subsets, what we can do is sum up over all subsets of particular sizes over all particular sizes of subsets. So for size of the subset being k, or from 0 through n, k is the subset size, we can then sum up all index sets that are of size k. So in class we defined the binomial coefficient for sets to be, if you have a set on top and a number down below, it's the set of all subsets of a particular size. Okay, so we just took the sum and made it be 2 steps. Then, now the thing is, when k is 0, we're taking all the 0 element sets. And as 0 elements, there's only one of them. It's the empty set. And if you take the product over the empty set, that is by definition 1. So the k equals 0 term is just 1. And there's a 1 out here, so we can cancel it out. So in this expression, we've started from 1 instead, because well, we're canceling out the 1 that started, or that it begins with when k is 0. And then we can pull this minus sign out to here. And there's a minus sign in front here too. So let's see. So we're multiplying together for every I in big I, a minus 1 times that. So if we pull the minus 1 out, it would be minus 1 to the k. And then, because it's a k element set, and so if we bring the minus 1 to the k out and make it negative, we can instead do minus 1 to the k plus 1. Okay, so then the next operation we can do to this is, there are 2 that I did. One, this is a product of Iverson brackets, so we can turn it into an Iverson bracket of ands, of conjunctions, and that is the same as being the Iverson bracket of x being in the intersection. And then also, the sum over x, whenever you have a sum, you can push it through sigmas as far in as you want, and I'm going to bring it all the way in, because that means that we've got this sum for subset sizes from 1 through n of minus 1 to the k plus 1 of the sum over all index sets of size k of then the cardinality of the intersection of those sets. So this is the general inclusion-exclusion formula. If you think about what's going on, when k is 1, we're adding, this will be positive, we're going to add together the cardinalities of each of the sets that are involved here. And then we're going to subtract all the cardinalities of the intersections of pairs of sets. Then we're going to add in the cardinality of the intersections of 3 sets, then subtract the cardinality of intersections of 4 sets, and so on until we get to n. And so, yeah, that's the inclusion-exclusion principle. Let's look at an example with 3 sets just to see how it all expands out. So I've reproduced the formula up in the right corner so we can take a look at it. And so for 3 sets, we can go from k is 1 through 3. So this is k equals 1, k equals 2, k equals 3. And so for the k equals 1 case, we're looking at all size 1 sets of cardinalities of intersections of that one set, so just the set itself. So we've got the sum over all size 1 sets, and then this, and then for the next one, k equals 2, it's going to be the sum over all size 2 subsets. And then for k equals 3, we're adding the sum over all size 3 subsets of triple intersections. And so if we enumerate everything here, we've got the sum over all cardinalities of one of the sets, minus cardinalities of the intersections of pairs of the sets, and then finally the intersection of the 3 sets cardinalities added to that. So that is the 3-set inclusion-exclusion principle. And let's check this by another way, just to verify that this makes any sense. So if we were to just add all the sets together, in this Venn diagram here, what I'm representing is how many times we count each region. So certainly we don't count outside the sets at all. And then so if this is S1 and this is S2 and this is S3, then when we add this all up, this region is counted once, but then this region that's in the intersection of S1 and S3 but is not in S2, that's counted twice. And then the part that's in the triple intersection is counted by all three of them. And the thing is, for this to be the cardinality of the union, we want each of the regions to be counted exactly once. So then for the k equals 2 correction, the exclusion, what happens is that, again, the outside is not counted at all, and everything on the inside is almost counted correctly, but the triple intersection is still it's counted 3 times. And if we were to, and that's because, well, it's covered by the, so the intersection of S1 and S2 is this region, S2 and S3 is this region, and S2 and S3, or S1 and S3 is this region. And the scribbles there are 3 scribbles overlapping the center. So if we were to then take the first minus the second, we'd have, oh wait, did I make a mistake here? Yeah, I meant to put, these are all zeros out here, because we're only counting intersections, and these are the parts that are only in S1 and not in the rest, right? So if we were to take the first diagram minus the second diagram, what we would get is 1, 1, 1, 1, 1, 1 with a 0 in the middle. And because there's that 0 in the middle, we're not counting the union correctly. So we need to have this additional correction. We're including this, and that's the 1 in the middle from the triple intersection. And then if we add that in, we get 1s uniformly in all the regions, meaning we count each region exactly once, with the outside region not counted at all, which is perfect. So just to summarize, I think the key idea behind all this is the following identity, that 1 minus the Iverson bracket of an OR of a bunch of expressions, of a bunch of propositions, can be written in this factorized form as 1 minus each of the propositions, and then those all multiplied together. Because then when we expand out this right-hand side, we can then, we get this formula where we can take the 1 minus each of the Iverson brackets, then plus products of pairs of Iverson brackets, minus products of triples of Iverson brackets, and so on. And these can each be interpreted as intersections of sets. Okay, so that's all for this video, and I'll see you next time.